Welcome back to our discussion of Fourier series. This is Muhammad Hawa. Let's continue our practice by solving more examples. For this example, start by drawing x of t, where x of t is repeat every 4 seconds, 2 delta t minus 2 over 2. Notice the time shift here. What you will get is this repeated triangular signal. This repeated triangular signal is shifted to the right by an amount of 2 seconds. Determine the complex exponential Fourier series, the trigonometric Fourier series, and the compact Fourier series forms for this example. As a change of pace, let's this time solve for the trigonometric Fourier series, the a-n's and the b-n's, and then convert the trigonometric form into the complex exponential form. Because this signal x of t is an even function, we only need to calculate the a-n's using this integral of x of t cosine and omega naught t dt over half period. Of course, remember to multiply by 4 over t naught. If I start my integral from 0 to t naught over 2, then the signal x of t is simply a linear line, as you can see here, from 0 to t naught over 2. And this linear line has a slope of a divided by t naught over 2, which means the slope is 2a over t naught. Its y-intercept is 0 because it passes through the origin. So I substitute for x of t, 2a over t naught t, that's the equation for the linear line. Multiply it by cosine and omega naught t dt. As usual, I'll solve this integral for a naught first, and then I'll solve the integral for a general n not equal 0. For a naught, substitute n equals 0 here and here. You get cosine 0 is 1, and that leaves us with 2a over t naught t. I can take this constant outside the integral. The integral of linear line t is t square over 2. You go from 0 to t naught over 2. If I substitute the limits, see here t naught over 2 square over 2 minus 0 square over 2. I'll notice that t naught square cancels out. The 2 square cancels out with the 4, and the 2 cancels out with the 2 here. I am left with a. So a naught is equal the amplitude a, which is equal to, in my case, if you divide a naught by 2, you get the DC value or the average value of the signal, which is a over 2, which is, by the way, the same as alpha naught, which is the 0th coefficient for the complex exponential Fourier series form. The answer a over 2 makes a lot of sense because the area under this triangle for one period of time is the height a multiplied by the width t naught. That's a multiplied by t naught multiplied by half. Now divide the area by the period t naught. You get a over 2, which is the average value we obtained by integration here. Now let's move on to evaluating this integral x of t by cosine and omega naught t dt for half a period for a general n not equal 0. I could take this constant 2a over t naught outside the integral, as you can see here. I'm left with the integral of the linear line t multiplied by cosine and omega naught t dt. This is an integral we can solve by parts. Remember the rule for integration by parts. And the integral t cosine constant a multiplied by t dt gives you this result, which is also cosine at, but divided by the constant square, plus the linear line t multiplied by sine at divided by the constant a. Please do the integration by part yourself and verify that this is the correct answer. So the result of this integral is cosine divided by the constant inside the cosine, which is n omega naught squared, plus t by sine. Remember, please, to divide by a, which is n omega naught. The next step is to substitute the limits in the result of the integral, which we do here. I'll start by substituting t naught over 2. Notice the cosine here is cosine n omega naught t naught over 2. plus I'll substitute t naught over 2 here as well. You get t naught over 2, and inside the sine you get sine n omega naught t naught over 2. And then minus, I'll substitute 0. 0 inside the cosine, you get cosine 0, that's 1. You're left with 1 over n omega naught square. If you substitute 0 here, you get 0. If you substitute 0 inside the sine, you get sine 0, also 0. So you don't get anything here. To simplify even further, remember that omega naught is 2 pi over t naught. T naught cancels out, the 2 cancels out. You're left with a pi here, so cosine n pi. Same thing for the sine. Substitute omega naught 2 pi over t naught, you get sine n pi. But notice that sine n pi, for n equal 1, you get sine pi. For n equal 2, you get sine 2 pi. For n equal 3, you get sine 3 pi, and so on. And all of those values are zeros. So this term actually disappears because it's always 0. And you're left with this term, cosine n pi, as you can see here, and minus 1, as you can see here. N omega naught square is a common factor that I can take outside, as you can clearly see. I'll say again that omega naught is 2 pi over t naught. So t naught square cancels out with the t naught and t naught here. 2 square cancels out with the 4. You're left with a pi, so you get n pi square, and you have 2a left, cosine n pi minus 1. That's the answer for the an's. Because the signal x of t is even, you don't have to evaluate the bn's. They will turn out to be 0. To give an even more detailed answer, I could substitute for n in the answer for n equal even and n equal odd. Notice that if n is equal even, 2, 4, 6 and so on, you get cosine 2 pi, cosine 4 pi, cosine 6 pi, and that's equal 1. 1 minus 1 cancels out, you end up with 0. So an is equal 0 when n is even. On the other hand, when n is odd value, you get cosine pi, cosine 3 pi, cosine 5 pi. That's negative 1. Negative 1 minus 1, you get minus 2. Multiply by this, you get minus 4a over n pi square, which is a negative value. Bn, as I said, is 0 for all values of n. This is the result for the trigonometric Fourier series expansion for our signal x of t that we considered in this example. And since I managed to calculate the trigonometric Fourier series, I can easily go to the other forms. I don't have to do the integration again. For example, alpha naught is a naught over 2. We know that a naught is a, so alpha naught, the DC value or the average value, is the amplitude a divided by 2. Alpha n for n not equal 0 is an over 2 minus jbn over 2. Bn is 0, so the imaginary part is 0. An, on the other hand, is 2a over n pi square cosine n pi minus 1. Of course, I divided by 2 here, so I get a over n pi square cosine n pi minus 1. That's the result for the complex exponential Fourier series form. And if you do the integral from scratch for alpha n, you'll be able to find the same result as this one. By the way, when it comes to complex exponential Fourier series form, I could use Fourier transform and Fourier series properties to quickly come up with the answer from the solution we had earlier for a general repeated triangular signal. And I hope you remember that for that general repeated triangular signal, we got alpha n equal a tau over t naught sinc square n omega naught tau over 2 pi. The difference between the general repeated triangular signal I solved earlier in the first example is that this triangular signal is symmetric around the y-axis. The two changes I made to get the third example is to increase tau to make it t naught over 2 and also to shift this repeated triangular signal to the right. As you can see in this diagram, the amount of shift to the right is t naught over 2. That's why the answer for this specific example is the same as the general example. I'll still get the sinc square that you can see here, but instead of a general tau, I'm going to substitute tau equal t naught over 2 as you can see here, and tau equal t naught over 2. Not only that, but I will multiply by this extra exponential because of the time shift. And the time shift is to the right, so I'll multiply by e to minus j and omega naught t naught, where t naught represents the shift of the fundamental period t naught over 2. So the answer for our specific third example is this value here, where t naught cancels out. T naught cancels out because omega naught is 2 pi over t naught. The 2 cancels out, the pi cancels out. I end up with a over 2 sec square n over 2 e2 minus j n pi. This is a complex number with this magnitude and this amount of phase shift. That is the answer I obtained from Fourier transform properties, but it's equivalent to the answer I obtained earlier from integration, and you can verify that by trying to substitute n equal 1, n equal 2, n equal 3, and finding alpha 1, alpha 2, alpha 3, alpha 4, and so on. You'll find it gives you the same exact complex number. For example, as a quick check, substitute n even here. When you substitute n even, you get sec of 2 over 2, that's sec 1, sec 4 over 2, that's sec 2, and then sec 3, sec 4, sec 5. Those are the nulls of the sec, which means you get alpha n equals 0. And I told you earlier that for n even, you get a n equals 0. Combined with b n equals 0, you're going to get 0 minus j0, alpha n's equal 0. Now you guys try the other case where n equal odd. Notice, for example, the square you get here for n pi. And also notice the square that you get here in the sec. Remember please that sec n over 2 is sine pi n over 2 divided by pi n over 2. But because you have the square, you have to square the numerator and denominator. So you'll get a similar answer to what we got earlier. Those are two methods to calculate the answer for alpha n, and you can see both of them are not that difficult to calculate. Finally, if you're interested in the compact Fourier series form, then you can find it either from the complex exponential form. For example, Cn is 2 absolute value of alpha n, the magnitude of alpha n, or you could say Cn is the square root of an square plus bn square. Since bn is 0, you get the absolute value of an. For theta n, it's negative of the angle of alpha n. Remember please that the angle of alpha n is minus n pi, so the angle theta n is actually equal n pi. Or alternatively, you could say tan inverse bn over an, you get tan inverse 0 over an. But please remember that in this specific example, for n even, we get alpha n zeros. For n equal odd, where n equal 1, 3, 5, and so on, n pi will be similar to pi. So we might see the answer written as pi. And the reason, of course, is that the an's are negative values. So the complex number for n equal odd has an angle of pi or 180 degrees. For n even, we get alpha n zeros. Now let me give you a homework to practice. For this x of t, repeat every 2, 6 delta t minus 0.5 minus 3. First, verify that the signal looks like this, which is a repeated triangular signal. But this time, it's not only positive values. This repeated triangular signal has sometimes positive values, sometimes negative values, because of the shift that I have here. Notice that this is an odd function, so you could use that to your advantage and start with the trigonometric form. Because odd signals in the trigonometric form have an equals 0 for all n, including a naught where n equals 0. So a naught is 0, an equals 0. The reason, by the way, a naught is 0 is that the positive area here and the negative area here are symmetric, which means they cancel out and you get the area under the curve equals 0, forcing the DC value or the DC shift or the average value to be 0. What you need is to find the integral for bn. Please find that integral. Here is the answer you're going to get. 8a over n pi square sine n pi over 2. And if you start substituting different n's, you notice that sine n pi over 2, where n equal 2, 4, 6, 8, and so on, is sine pi or sine 2 pi and so on. This is actually equal 0, and you end up with 0 value. For n equal odd, on the other hand, sometimes you'll end up with positive 8a over n pi square, or sometimes you'll end up with negative 8a over n pi square, depending on what you get for the sign, sometimes positive 1, sometimes negative 1. depending on the actual value of n. So please do the integral, verify that this is the answer you're going to get. From that answer, you can get alpha naught, which is a naught over 2, and you can also get alpha n, which is a n over 2 minus j b n over 2, and you notice that this is a purely imaginary value for alpha n. Alternatively, you could try Fourier transform and Fourier series properties to come up with the solution for this specific example based on the solution we had for a generic repeated triangular signal, which I hope you already memorized. Alpha n equal a tau over t naught sinc square and omega naught tau over 2 pi. However, notice here I modified my answer because of the changes I made between the general repeated triangular signal and this specific repeated triangular example. See, in the general case, my amplitude was A and my signal was all positive. What I did to go from this general case to the more specific example is double the amplitude. Notice this is A and minus A. So the amplitude peak to peak is actually 2A. And then once I got to A triangular signal, I dropped the signal by a shift of minus A, which is minus 3 here. So I scaled my amplitude by a factor of 2, and then I introduced amplitude shift downward by a value of minus 3. Not only that, I did a shift of the signal to the right by a quarter period. That's why if you want to use the generic solution, you have to be careful about those modifications. For example, notice instead of A, I'm using 2A here. That's because of amplitude scaling that I did. Notice also that I multiplied by e2 minus j and omega naught t naught, where t naught is a quarter period because I did a time shift. And that's the answer I get for my specific example, which is, by the way, the same exact answer that you get here. The n by square, by the way, comes in from inside the sinc square, and the sign comes in from e2 minus j because e2 minus j is cosine minus j sine. Somebody might say, what about the amplitude shifting? What is the effect of amplitude shifting of minus a, minus a 3 on those alpha n's? Well, I'll tell you later on that only alpha naught is affected by the DC shift, not any other n. That's why alpha naught here, which is equal a sinc square 0, sinc square 0 is 1, e2 minus j 0, e to 0 is 1, so you get a, and then you subtract minus a, the amount of amplitude shift. That's why alpha naught turned out to be 0. But all the other alpha n's, alpha 1, alpha 2, alpha 3, alpha 4, are not affected by the amplitude shifting. Finally, if you want the compact form Cn, then Cn is 2 times the absolute value of alpha n. And you could read the absolute value of alpha n either from here, the absolute value of this complex number, or you could take this absolute value of this complex number. Both are valid. For the angle, you could take the angle here, or you take the angle of this complex number, which is either minus pi over 2 or pi over 2, dependent on do we get positive 1 or minus 1 from this sign. So we get either positive j or minus j complex number, and we get, dependent on that, the phase shift of minus pi over 2 or pi over 2, which is minus 90 degrees or plus 90 degrees. Please first solve the problem yourself, get the trigonometric form, the complex exponential form, the compact form, and then compare your answers to my answers here. The last example I want to go through in this video is this signal, which is x of t, repeat every period t naught, a delta of t. This is the Dirac delta function or the impulse function. So I get every period t naught an impulse. You see here an impulse, 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 and so on. This is an impulse train, a very important signal. I know it's ideal signal, but it's quite helpful in our math development in this course. So I say to you, all right, take this x of t and find the Fourier series, the complex exponential Fourier series, the trigonometric Fourier series, and the compact Fourier series. This is actually a very simple problem to solve. So if you want to solve the complex exponential Fourier series, then you have to evaluate alpha n using 1 over t naught, the integral over 1 period x of t e2 minus j and omega naught t dt. Where if you do the integral from minus t naught over 2 to t naught over 2, x of t is the impulse function. In this particular example, I scaled the area under the impulse delta t by a factor of a, but this doesn't change much because I can take a outside the integral. So I get the integral of delta of t by e2 minus j and omega naught t dt. Instead of finding alpha naught separately from alpha n, I'm going to find alpha n for all n using a very important property for the impulse function called the sampling property, which I want you to memorize. This is a well-known property of impulse functions. Some people even use it to define the impulse function in the first place. The sampling property says the integral of x of t by delta of t minus t naught dt is equal x of t naught. So if you multiply any function by an impulse function located at time t naught, what you get is the value of the function at t naught. Why is that? Because x of t, when multiplied by delta, you multiply by 0 everywhere except at t naught where the impulse is. And you multiply by an area of 1. That's why x of t naught is the only value of x that survives, which you can take outside the integral. And the integral of delta is 1. So you get x of t naught. So the impulse samples your signal at a certain point where the impulse is located. We could use this to our advantage to evaluate this integral because the impulse here, delta of t, is located at 0. So it is sampling this function at time equals 0. And that's why the integral of delta of t, e2 minus j and omega naught t dt, is the value of this function, e2 minus j and omega naught t, when t is equal the value where the impulse is. And that impulse is located at 0, so you use t equals 0 here. Of course, e to the power 0 is 1, and you're left with this constant a over t naught. Hence, we prove that the complex exponential Fourier series coefficients for this impulse train or repeated a delta of t is equal to the area under the impulse a divided by the fundamental period t naught. And this applies for all the alphas. Alpha 0, a over t naught. Alpha 1, a over t naught. Alpha 5, a over t naught. Alpha minus 4, a over t naught. All the alphas are constant and they are equal to the area a divided by the fundamental period t naught. By the way, a is a real value, t naught is a real value. They are both positive values. That's why the absolute value of this complex number alpha n is a over t naught, and the phase shift of that complex number is 0 degrees. Alpha minus n has similar value a over t naught, and the angle of alpha minus n is equal minus 0 degrees, which is also 0 degrees. If somebody says, how about the trigonometric form? Well, you can get the trigonometric form from the complex exponential form, because alpha n is a n over 2 minus j b n over 2, and I know that alpha n is a over t naught, that's a real value, so b n's are 0. b n's are 0, as you can see here, which, by the way, makes sense because this signal is even signal. Please remember that the impulse, as you can see here, located at 0, is considered even function, even though the width of that function is, strictly speaking, 0 seconds. On the other hand, a_n's are 2 multiplied by a over t naught, 2a over t naught, as you can see here. This includes a0 as well. That's all for this video. Please make sure you practice by solving even more problems for Fourier series, the complex exponential form, the trigonometric form, the compact form. The best way to understand Fourier series is to solve problems. So I encourage you to find even more examples and solve them. In the next lecture, we'll try to visualize the alpha n's and the cn's using magnitude spectrum and phase spectrum. If you have questions, please use the comment section. Goodbye.